We've ended the last video with this final form for the Hamilton Jacobi equation, this one right here. In this video, we're gonna see how to solve this Hamilton Jacobi equation. But first of all, we have to notice that this equation right here is a first order nonlinear partial differential equation. And in general, it's gonna have a complicated solution. We're actually due to the fact that there is like variables included in this vector here. And there's like one more variable included in here that is the t variable. So there's like in total n plus one variable in this equation. So this permits us to write down a solution for this equation in the following form: a solution which contains n plus one constants in the following form: s plus alpha subscript n plus one. The s function, or the derivative function, or the complete integral, contains n constant, and those n constant are included in this vector here, the alpha vector in here, right? And this like alpha here, this alpha subscript n plus one is this like the constant number n plus one, right? But actually, like, we can simplify this solution once more by just like noticing that this s is included only by its time derivative in this equation, like in this Hamilton Jacobi equation. So that means we can draw the constant, this constant right here, and be satisfied with just getting s, with just getting an s. So once you get the s, which satisfies the Hamilton Jacobi equation, you're done. You've solved you solved it for the dynamical system you're after. After that, we just like plug in the two equations we pulled out of the box, or out of the hat, in the last video. If you remember them, the first one says that partial s partial q vector q small equals the vector b, right? And the other one says that, let's just like write down here, partial s partial p capital equals q capital, right? But actually, as we've said, this p capital actually is a constant vector. It's equal to alpha, the vector alpha. And in the same way, this q vector is a constant vector. It's equal to the vector beta. So that means we can rewrite down this second equation here in a more different form. That is, the new, we're just like gonna take each p and put alpha, stuff like that. Partial alpha equals beta, and that's the second equation. So what we're gonna do after we get the s is just to substitute first in this equation right here, this equation, and solve this equation for q, the first canonical variable we're after. So that like implies we're gonna get q as the vector q as a function of beta and alpha, right? No. Alpha, beta, and t, right? After that, we're gonna plug in with this s in this equation right here, not this equation right here, the other equation, the first one, this equation right here. And we're gonna solve this equation for p, and this will get us p, the other canonical variable we're after. We're after those two canonical variables, the p and the q. It's gonna give us the p as a function of alpha and beta and t as well. So that's it. We've solved the dynamical problem. We solved our dynamical problem just like by getting the s and plugging in those two equations right here. So actually, I want to mention like a special s which is gonna solve a special kind of problems, and we're gonna use this in the work of Schrödinger when we get to that. Okay, if we have the Hamilton Jacobi equation written down in this form, h as a function of q, the vector q, and partial s partial q, but there's no time dependence, plus partial s partial t equals 0. This tells us actually that we can write down s in the following form. That's form for s, which is going to solve our Hamilton Jacobi equation. W as a function of q, only the space as a function of space, minus alpha, which is a constant, times t. And that actually is a really important form we have to remember, because we're going to use this when we get to Schrödinger's work. So that was it for this video. Thanks for watching.